So today we're going to continue our discussion of very long instruction word processors. And we're going to start talking about how to change a classical VLIW processor into a processor which can actually get a lot of the parallelism and instruction level parallelism you can get inside of out-of-order superscalars. And to do this, we're going to have to add a lot of extra features to a traditional or a classical VLIW. And we're going to slowly work through that. And we're going to basically list out or enumerate all of the possible different types of instruction level parallelism and where that comes from in something like an out-of-order superscalar. And we're going to systematically add features into a very long instruction word processor or VLIW processor to get us to that point. But I'll give you a hint that not all the things that out-of-order superscalars can get are easy to get in VLIW processors or even possible in the realm of things that people have built up to this point. So before we do that, I wanted to take a step back and review something from last class and also review something from, I wanted to clarify something that I had said about how the EQ model and the LEQ model, or the equals model or the LEQ model, work from a scheduling perspective. So let's back up to slides way back at the beginning. And more of what I wanted to say was just a comment that the equals model of VLIW scheduling and the less than or equals scheduling model are just scheduling models. That's all they are. They're not actually something that's in the hardware. They may influence what the hardware has to do or what the hardware has to provide. So for instance, if you have an equals model and you have an instruction followed by another instruction in your very long instruction word processor, and let's say the instruction reads the value of some register in sort of the shadow of while that value is being computed, you're going to get the old value in an EQ model. So as a quick code example here, we can take a look at a bundle of instructions here. Let's say you have something like a multiply, R1, R3, R4, and in the same bundle or in the same VLIW instruction, we have some other random thing here. We're going to use the curly braces here to denote that it's one instruction or one bundle. And then this multiply, we'll say, has a latency of 4 cycles. So you can't actually go read the result. And if you look at something like an EQ model, we're going to end up with, let's say we just have some other instructions in here. But this one here is important. We have an add. Which reads R1. Note this multiply writes R1. But as we said, the multiply has a latency of 4 cycles. So this, in the EQ model, is going to get the value before the multiply. So it's not going to pick up this result. And then, let's say we just have some other random stuff. I don't know, maybe some non-dependent adds and subtracts. And I'm not going to write the registers here because they don't read anything or write anything which is read or written in these two bundles. Maybe you have a no-op. And then finally, down here, we have something which does a load of R1 and gets the result of this multiply. So all I'm trying to get across here is this is a scheduling model of what the compiler needs to do and where it needs to place code that we're talking about in these scheduler models. It's not a hardware problem. If we were to try and take the same piece of code and run it in an LEQ model, the main difference is this add here, which reads R1, would not be allowed in the shadow here. So what would the shadow of this multiply, or the delay of the multiply? Because if you were to, for instance, take an interrupt or something like that, and this add were to get moved later than this load, or move more than 4 cycles later, or 3 cycles later, you would actually pick up the new value, and you'd basically change the semantics of your program. So if you were to do this in something like a LEQ model, this add would have to be above the multiply, and you'd have to replace this with a no-op. But more of what I'm trying to get across here is that these are just scheduling models and not actually scheduling models that the compiler wants to use, and not models, or not hardware models. The hardware has to implement something which makes sense for the scheduler model, but when we talk about these different concepts, they really are just a software scheduler model. OK, so now we're going to go back forward here and move on to new content today.